Hello everyone, welcome to Mathematics Step by Step. I am Ying. So today we'll learn to verify the formula of probability of combined events for mutually exclusive and non-mutually exclusive events, okay? So first of all, let's go through this mind stimulation 5 together. So you can have this discussion with your friends also. So the case is as follows. Fahmi holds an open house in conjunction of the Aidilfitri celebration. 80 guests come to the open house. 2/5 of the guests who come are Fahmi's colleagues. Okay, so 2/5 out of 80. So 32 of them. There are 55 guests who come together with their family members. 18 of them are Fahmi's colleagues. So 1/10 of the guests who come are Fahmi's children's schoolmates. So 8 of them. All of Fahmi's children's schoolmates do not come with their family members. A guest who comes with Fahmi's open house is selected at random. Let's see, these are the three events, okay? A is the event that a guest chosen comes with family members. B is the event that a guest chosen is Fahmi's colleague. C is the event that a guest chosen is Fahmi's children's schoolmates. So we know that event C and event A are mutually exclusive, okay? So I'll assume this is set C, okay? Because given that all of Fahmi's children's schoolmates do not come with their family members, okay? So we know there are 32 of them are Fahmi's colleague, okay? And then out of the 55 guests who come together with their family, 18 of them are Fahmi's colleague. B is the event that a guest chosen is Fahmi's colleague. So from this sentence, we know that event A and event B are non-mutually exclusive. Okay, so I would assume event B is like this. Okay, event B and event C are also non-mutually exclusive because the guest chosen, if let's say is Fahmi's colleague, then the guest is not possible to be Fahmi's children's schoolmate. Okay, so we know that there are 18 out of 55 of them who come with their family is Fahmi's colleague. Okay, so we know here is 18. Then here is 55 minus 18, which is 37. Okay, so that 37 plus 18 gives us 55. Okay, so for event B, we know total there are 32 of them. So here is 32 minus 18 give us 14. Okay, so now we know there are 8 of them here in set C. Okay, so now let's add up. 37 plus 18 plus 14 plus 8 equals to 77. Okay, so here is 3. So based on the Venn diagram drawn, complete the following table. Probability of getting A, meaning probability of getting a guess from this set. Okay, so is 55 out of 80. Okay, then probability of getting B is the probability of getting a guess out of this set. So is 18 plus 14, so is 32/80. Okay, then probability of getting A and B is the probability of getting guess out of this part, okay, which is the intersection of set A and set B, so is 18/80. Then the probability of getting A or B is probability of getting guess out of this set. Okay, so 37 plus 18 plus 14 equals to 69. So 69 out of 80. Okay, so now let's proceed to B. Probability of getting A is 55/80. Then probability of getting C is 8 out of 80. Okay, then probability of getting A and C is 0. Okay, because event A and event C are mutually exclusive. Okay, they will not happen together. Then probability of getting A or C is 37 plus 18 plus 8. A is here, C is here, okay? So we add up. So 63 over 80, okay? Then let's proceed to C. Probability of getting B is 18 plus 14 out of 80, which is 32 over 80. Then probability of getting C is 8 over 80. Probability of getting B and C is 0 again, because event B and event C are mutually exclusive. Then probability of getting B or C is B is here, C is here. So we add up, okay? 18 plus 14 plus 8 equals to 40, okay? So 40 out of 80, okay? So from the activity in mind stimulation 5, it is found that number 1, probability of getting A and B, probability of getting A and C, and probability of getting B and C are identified first so that we can determine whether the combined events are mutually exclusive or non-mutually exclusive, okay? When there are intersection between the two sets, then they are non-mutually exclusive, okay? Then when their intersection is 0, so they are mutually exclusive, okay? Part 2. The combined event A and B is non-mutually exclusive because probability of getting A intersect B is not equals to 0, okay? As we can see here, 18 over 80. Then probability of getting A or B equals to probability of A plus probability of B minus probability of A intersect B, okay? So later on, we will use this formula quite frequently, okay? Let's check for the case of 4A. Probability of A is 55 over 80. Probability of B is 32 over 80. Then probability of getting A intersect B is 18 over 80, okay? We learn to apply the formula and we want to check and see we are getting the right answer. So yeah, equals to 69 over 80, which is the same answer as we have found just now, okay? Then 2B, the combined event A and C and combined event B and C are both mutually exclusive, okay? As we have discussed just now, because probability of getting A intersect C equals to 0 and probability of getting B intersect C is 0. Then probability of getting A or C equals to probability of A plus probability of C only, okay? We don't need to minus the intersection because it is equals to 0, okay? Same goes to probability of B plus probability of C equals to probability of B or C, okay? So the addition rule of probability is probability of A union B equals to probability of A plus probability of B, or probability of A union B equals to probability of A plus probability of B minus the intersection of the two sets, okay? So depends on the situation. Sometimes we will use this formula, sometimes we will use this formula, okay? So we have to learn to differentiate between mutually exclusive and non-mutually exclusive events, okay? So now let's go through this example 7 together. The Venn diagram on the right shows the relationship between the universal set A, B, and C, okay? A number is chosen at random from the universal set. Verify the addition rule of probability for each of the following combined events. 8. Obtaining an even number or a multiple of 5. Okay, so we know these two events are non-mutually exclusive. So the intersection of the two events is equals to 0. So that's why we apply this formula, okay? So first of all, let's check probability of getting A union B, okay? Or, so that's why it is union, equals to the number of elements in the set A union B. So A is here, B is here. We can see there are 5 elements, okay? Then number of elements in the sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? 9 of them. So now we apply this formula and we want to check and see are we getting the same answer. So probability of getting A is 4 out of 9. Then probability of getting B is 1 out of 9. So we add up, we get 5 over 9. So it is proven that probability of getting A union B is equals to probability of getting A plus probability of getting B, okay? Then part B, obtaining an even number or a prime number. So in this case, it is non-mutually exclusive, okay? We can see that there is intersection between set A and set C now, okay? So again, we'll first find probability of getting A union C. So probability of getting A union C is the number of elements in A union C divide the number of elements in the sample space. So the number of elements in set A union C is here, okay? So we can see there are 7 of them. So 7 divided by 9, okay? Then we will apply this formula. There is minus probability of getting A intersect C here because in this case it is non-mutually exclusive, okay? So probability of getting A is 4 out of 9. Then probability of getting C is 4 out of 9. Then minus the intersection. So one element here, so 1 over 9. So the answer is 7 over 9. Again, it is proven that probability of getting A union C is equals to probability of getting A plus probability of getting C minus probability of getting A intersect C, okay? So now let's go through example 8 together. 8 cards labeled with the numbers 4, 5, 6, 7, 8, 9, 10, 11 are put in a box. A card is chosen at random from the box. A is the event of getting a number greater than 8. So 9, 10, 11. B is the event of getting a prime number, so 5, 7, 11. Then C is the event of getting an even number, so 4, 6, 8, 10. Verify the addition rule of probability for each of the following combined events by listing all the possible outcomes. So A, probability of getting A or B. So now we can see that set A and set B, they are non-mutually exclusive, okay? Because we can see there are common elements, okay? So A intersect B equals to 11. So now we apply this formula, okay? Probability of getting A is 3 out of 8, okay? Because there are 8 of them in the universal set. So we can see 3 over 8 here. Then probability of getting B is also 3 elements here out of 8. So 3 over 8. Then the intersection, there's only one common value in these two sets, so 1 over 8, okay? So we get the answer 5 over 8. Then now, we want to list all the possible outcomes in this case. A or B. So we have found A, we have found B. So A union B is 5, 7, 9, 10, 11, okay? Although 11 is in both sets, but we will write the common elements only once, okay? So 5 elements out of 8. So again, we get the same answer. So proven that probability of A plus probability of B minus probability of A intersect B is equals to probability of A union B, okay? So now let's proceed to B. Probability of getting A or C. So we can see that event A and event C are non-mutually exclusive, okay? Because again, there is common elements in these two sets, okay? So non-mutually exclusive, and we'll apply this formula. So there's only one common element in the intersection, so 1 out of 8. Then probability of getting A is 3 out of 8. Probability of getting C. You can see here there are 4 elements in this set. So 4 out of 8, and we get the answer 3 over 4. So now we want to list all the possible outcomes. So A union C is 4, 6, 8, 9, 10, 11. Okay, there are 6 of them, so 6 out of 8. Again, we get the same answer. And it is proven that probability of getting A plus probability of getting C minus probability of getting A intersect C is equals to probability of getting A union C, okay? So now, let's proceed to part C. Probability of getting B or C. So now, we can see that set B and set C, there is no common elements. So they are mutually exclusive. Okay? We can see that the intersection is an empty set. So we apply this formula. We don't need to minus the intersection, okay? So probability of getting B is 3 over 8. Probability of getting C is 4 over 8. And we add up, we get 7 over 8. Then now we want to list all the possible outcomes. So set B union C is 4, 5, 6, 7, 8, 10, 11. So there are 7 elements out of 8. Again, we get the same answer. So it is proven that probability of getting B plus probability of getting C is equals to probability of getting B union C, okay? So now today we have learned a lot of things. So go back, you guys will complete this self-practice 9.3b, okay? So if you are struggling, you are having a lot of difficulty in completing all these self-practices in the textbook, I have prepared an online course for you guys. It is a step-by-step guideline in helping you guys to complete all these self-practices in the textbook, including the comprehensive practice at the back of each chapter, okay? So coming next, we'll learn to determine the probability of combined events for mutually exclusive and non-mutually exclusive events, okay? So do not forget to subscribe to my YouTube channel so that you do not miss out any of my upcoming videos, okay? I'll see you in the next video. Bye bye.